Okay, so just a little bit of who I am. I'm an electrical engineer from Universidad de Antioquia at my home country in Colombia in South America. I focused on the digital signal processing there. Then I came here, I went to Columbia Engineering, and I did my master's in applied mathematics, and I was like mainly focused on computational science and engineering. And then I've been working for almost 2 years at Descartes Labs. Descartes Labs is an spin-off Los Alamos National Lab. So our headquarters are based in New Mexico, but we have a small office of scientists and engineers here. I work at the commodities team, so I spend a lot of my time trying to figure out how to process remote sensing data from satellites and sensors in general, how to process all this data efficiently. I focus particularly on the commodities team on things like crop modeling, how weather forecasts can affect many of the supply chain processes. So this is more or less what I do. I just wanted to put this quote here, all models are wrong, but some are useful. This is relevant to today's talk because when we build a model, and particularly a computational model, we leave out a lot of details. We have to make a lot of approximations, a lot of assumptions. So basically what we want to achieve is how wrong my model can be before being totally useless. So how wrong can be in terms of convergence, in terms of error metrics, in terms of bounds. So that's a little bit of what these models that we're going to talk about today, we want to achieve with these new methodologies. So I'm just going to go over some definitions that are in the paper. So first of all, what is a transition matrix? So it's this matrix whose product with the initial state vector produces the same state vector at a later time. So it's a matrix that I use to propagate in time steps my state vector. This is not the same, even though we're going to talk about the stochastic processes, transition matrix is not an stochastic matrix, which is just the transition probabilities in a Markov chain. The processes that we're going to talk about here are not Markovian because my processes are going to depend on my entire past, not only my previous time step is going to depend on more time steps. So it's very important to notice here that the transition matrix is time invariant. In general, it could be at some point time dependent, but for the purposes of this paper, it's time invariant. So it's not going to change over time. Second definition, what is a vector autoregressive model, known as VAR? So it's a model that captures linear interdependencies among multiple time series or multivariable time series. So each variable evolves based in its own lagged values and lagged values of other variables and some error terms and some constants. So we see here that, let's say this my variable y at time t, it can be represented as A1, which is my transition matrix that we're going to see later, at time t minus 1 plus A2 multiplied by y at time t minus 2, etc. So we can do this for p time steps. We have an error term here and a constant. So this is when we see that vector autoregressive is definitely not Markovian process, but rather depends on multiple values of my variable in the past. So this is what we can call like a lag P vector autoregressive model. In the paper, we're just going to talk about a lag 1 model. So basically, we're just going to have this first term here. You can see my pointer. So we're just going to neglect all these other terms and just going to focus on this first term here. There's another definition on the paper, like a spectral norm. What is a spectral norm? So it's basically the maximum singular value of a matrix, or in other terms, the maximum scale by which the matrix can stretch a vector when I take the product of the matrix and whatever vector. So it's just like a fancy way to name the natural norm in a matrix induced by the L2 norm. L2 norm in a vector induces the spectral norm in a matrix. So it's the same thing as saying a Frobenius norm, and it's the same thing that saying the induced L2 norm. So that's the spectral norm the paper is talking about. Another concept that the paper mentions in several different parts, what is a stationary process? So it's basically an stochastic process. This is like a long definition in whose unconditional joint probability distribution does not change over time. In other words, mean and variance don't change over time. That's it. So as you might imagine, there's a lot of processes in nature and in the world in general that are non-stationary. But as we do always in computer science and engineering world, we approximate nonlinear things to be linear, and we approximate non-stationary processes to be stationary. So one of the main, like the most common cause of non-stationary processes are trend in time series. So just imagine like a time series of prices, and they tend to go to, if prices tend to increase over time, the mean and probably the variance tend to increase over time. So this is definitely a non-stationary process, but we can fix that very easily, just like kind of subtracting a moving average over time. So it's like always like trying to, this is like part of the model, like trying to simplify things and make things that are not stationary become stationary. So that's part of how we build these kind of models. What is marginal and lagged covariance? So marginal is basically the opposite to conditional covariance. So it's just a direct representation of my time series, of the covariance of my time series. So we're going to see the formula later, but just relies on the marginal distribution of my variables. It doesn't depend on conditional distribution with respect to other variables. And lagged covariance is just the covariance of the time series itself with the time series lagged by some amount of time steps. So what is the purpose of trying to estimate a transition matrix? So when we have a physical system, it can be just we want to estimate how, like, equations of movement of a ball or something. So we know how to model this using equations. We have the equations that govern our system. So we know how to represent this in matrix form. And we have x, y, z position. Derivatives of x, y, z are velocity. Derivatives of velocity are acceleration, and we can represent this as a linear system and calculate our transition matrix in a closed form. But if we have nonlinearities, or we have absolutely no idea of the dynamics, the underlying dynamics of our system, so the best we can do is have a good estimator of our transition matrix. So this is why we're like trying to estimate this transition matrix. So what we want to prove with this paper is that the proposition being made on this paper is like we're going to use a method of calculating the transition matrix for a VAR model that is where the error is smaller than when we're calculating the transition matrix using just linear least squares estimators and ridge or lasso penalties that are basically, as the paper mentions, penalties based on one norm or two induced norm. And like the second thing is very important. We want to show that the error with respect to the true transition matrix is bounded. We don't want to have a transition matrix that at some point in time is just going to blow up. So we want this error to be bounded. So that's that's the introduction to the introduction. And now we go to the introduction of the paper. So let's say that we have this time series with the capital X. We're basically representing that this is a multivariable time series. So we have x1, x2 to xt, where x sub t, we are just going to use real domain here. So it's in the reals, and we have like d number of variables or d dimensions. And we are assuming that we have this stationary process here from t equals 1 to capital T, and is distributed normally with zero mean and this sigma covariance matrix. This is like our first assumption. So we are going to use a VAR model that is just like lag1 VAR model. We're going to use just one time step in the past to predict the future. So we have x at time t plus 1 is equal to my transition matrix A transpose multiplied by my previous value of my time series plus ct. This is a noise term that we're introducing. Here A is in the domain of reals, a square matrix d by d in the domain of the reals. And my noise term is distributed normally too with zero mean and this psi covariance. And we also assume that C and X are independent. So they, yes, they are independent variables. We are going to need that assumption to go through a proof of a proposition later. And there's some point being made here that to conserve the property of stationary, we have sigma, our sigma covariance matrix have to be in this form. So that's like, those are all the assumptions we're making to go through the paper. So what is normally used to estimate these transition matrices? So we always use like least squares estimator with different penalties. So it's basically trying to minimize over all matrices M that are in the space of matrices d by d. We're just trying to minimize this norm, which is just the Frobenius norm, the induced L2 norm in matrices. We're just like trying to minimize this operation here. And X is just my normal random variable, and Y is going to be my lagged one variable. So this is what we're trying to minimize. This it's very easy, but it's not very accurate sometimes. And for when D is kind of large, it can be computationally expensive. So this is like one of, they mention other methods in the paper. They don't go through the details, but they mention like instead using, this is the ridge penalty, by the way. We can also use the lasso penalty, which is using the L1 induced norm. They mention here to the Lyapunov penalty that I don't really know what it is, but It must be something fancier, I guess. But they mentioned that they don't get really good results when D is much larger than T, so I have more dimensions than time steps. So the main goal of this estimator is to find a way that I can bound my error in this way. So this is the big O notations for probabilities. So it's just like the probability of this being bounded by this expression is P in this case. So we want to have an L1 norm bounded and a max norm bounded. So both of them are bounded here. Oh, an important thing, this S term is mentioned somewhere in the introduction, so it's like a kind of a sparsity term. So it's just like telling us how many, like this is the number of non-zero terms that we have in a single row. So this sparsity terms comes in here, and here when I'm just using my max, my infinity induced norm, it just disappears. But this is the objective, that there's like the probability that maximize the probability that my error term, this is my estimator and this is my true transition matrix. The probability that this is bounded is high. So that's what we want to do. Okay, so they do later in the background, they are like kind of explaining a little bit what are the induced norms in matrices. So they are called induced because we know how to calculate the norm of a vector, but it's not the same that calculating the norm of a matrix. So for a number q between 1 and infinity, we say that our induced q norm in this case is like looking at all vectors whose q norm is 1, so like unitary vectors in this norm, it's like the maximum value of the product of this matrix and this vector. So when we induce the Frobenius norm, or like the second norm, L2 norm is going to be something like this. And this is the one that we're going to use for as a spectral norm. Okay, so that's in the background. Then we go to proposition 1, which is like the core concept of the paper, because what we want to do is represent or find or leverage the relation between the covariance matrix and the lagged one covariance matrix, and the relations of these two with my transition matrix. So this is the proposition. Suppose that we have this stationary process represented by this expression here, and we're going to define, like for this, the second expression is the one that is more important, like my covariance sub I is going to be the covariance between my process at time t and my process at time t plus I for any I between 1 and t minus 1. So we want to demonstrate that this thing here that is equal to A transpose to the power of I multiplied by the marginal covariance, that this is true. And then we want to basically estimate A based on my lagged one covariance here and my marginal covariance. So that's the objective. So this is the proof that I didn't really have time to put it in LaTeX format. So it's just like handwritten. So it's like just very easy. It's just like we want to just use this expression here to calculate x at t plus 1 plus I, sorry. So, and we just want to do this recursively until we get this result right here, and then we calculate the covariance between xt and this result that I got here. So there's two things here where the independence of the noise and the transition on the transition matrix and the random variable is important, because when I calculate the covariance, these terms goes out. This terms A transpose to the power of I goes out. And then the covariance of xt and my noise term is 0 because they're independent. So I end up, I end up with the covariance of xt and xt, which is my sigma, my marginal covariance. So from that result, we just can kind of plug when I is equals 1. So I get this result from here, and then I can just get an expression for A. So I just invert this one and transpose this other one, and I get my result A. So this is basically the result that we want to use for the rest of the paper. Okay, so we go now to section 3. And in section 3, we have the definitions for, in matrix form, for the marginal covariance matrix and lagged one covariance matrix. So it's basically this. This is just my normal random variable x, and this is my variable x lagged by 1 time step. So this is the two definitions that we're going to use. And then using proposition 2.1 results, we are just going to turn this into a minimization problem, which is going to be, okay, I'm just going to plug my A results in here. The result that I got right here, this one. But instead using sigma and sigma sub 1, I'm just going to use S and S sub 1. I'm just going to find a matrix M over all the domain of matrices, real matrices D by D that are subject to this constraint. And they mentioned that this lambda sub 0 is a tuning parameter that we still don't know, but we're going to find which is the optimal lambda 0 that minimizes all these expressions. So this is the problem we want to solve now. They also show here that we can, that it's equivalent to calculate this, oh, there's one bar missing here, equivalent to calculate A column by column. So they just like showing here that if I take this vector beta sub j hat, I'm just going to minimize this over the domain of vectors, real vectors of dimension D, subject to this constraint. So it's like splitting the problem in a smaller dimensional problem. So it's just like calculating this column by column. So I'm just like going like column 1, column 2, column 3, and then I just reconstruct my A hat, my approximation, using each of one of these vectors. So
is that star convolution?
No, it's just like a placeholder for all rows and one column, J column. Okay, so now they're going to start like making some tricks here to make this problem a little bit more, like the representation of this problem a little bit more towards a linear program with some constraints. So we can decompose this vector V into a positive and negative part, because we know this belongs to the real domain. So we know that this is like kind of an indicator function that I'm going to take the positive part, all elements that are larger or equal than 0. The negative part is elements less than 0. And we kind of go back to the minimization problem here, replace V with the decomposition into positive and negative parts. And I update my constraints here. So I'm just going to minimize this problem now. And my constraints become these right now. So is this? OK, there's actually a typo here. This should be a plus, because what I'm trying to minimize is the absolute value in this case. And when I take the absolute value of these, this becomes a plus. So there's a typo here. OK. Yeah, so I have now a new minimization problem with 2 constraints. And now what the final step is just like trying to represent this in matrix form and like a more compact way. So we're just going to represent V plus and V minus as omega. Theta is going to be my constraints, like part of my constraints, and W is going to be like this symmetric matrix using my marginal covariance matrices. So basically, the part 3 of this paper, the conclusion is like, OK, we transform all my problem into this linear program that we're going to solve with this constraint here, with just one constraint. OK, so in part 4, so the main results of part 4 is that we're going to state why this result is important. So we basically have a class of matrices here that this like funny M represented is a class of matrices with this parameter Q, this sparsity parameter S, and this MD quantity here that is supposed to be a quantity that grows with D, but it's not like very clearly stated what this MD can be. It's just that it says literally, let MD be a quantity which may scale with the dimensionality D. So it's not super clear about what is MD. But it's basically a class of matrices that this maximization, this max norm here is less or equals than S, than my sparsity parameter. It's just like a bound that we're using for M, this matrix M. So it's like we always want to have bounded matrices, so it's just kind of a bound that might increase with dimensionality. So as my matrix gets larger and larger, my norm, L1 induced norm can be increasing. So what they state here, okay, is that theorem 4.1 is that using these tuning parameter lambda sub 0, we can make sure that with probability larger than 1 minus 14, 1 over D, we have this bound for my error term. So there are 2 things here that are very important. In the introduction, they mentioned that the spectral norm of my true A is very important here, because we have these on my denominator, and these, like, if I have like my denominator can grow or shrink depending on the spectral norm of my matrix A. But the important result here is that my error is bounded. So no matter how many time steps I'm going ahead, this error is going to be bounded at this estimation, or my system is not going to diverge at any point. So this is very, very, very important. Okay. Okay, no. So this is basically the conclusion of the paper, that this the result is that we have this bound with probability, as stated here. There's a corollary that mentions that we can recover the support of the matrix if my matrix belongs to some class of matrices that has 0 here. So this is basically a type of matrices that they mention in the beginning that are sparse matrices with, well, they mention this class somewhere in the paper, but the important part is that we can recover the support of the matrix easily. The support means that we get the sign correct for each element of the matrix. So that's another important result. And they are just like showing, I didn't even put like all this, maybe if you can take a look later, there's like a bunch of tables that they show, they compare results with different random matrices that are banded or are like very different patterns of matrices that are distributed normally with 0 mean. So they just compare, like, as d increases, as t increases, how the ridge penalty using least square estimator, what's the error, and they just compare the results with the linear programming problem that we got here. And yeah, the conclusion is that this method, like, besides being very stable because my error is not going to diverge, the error is way smaller in some cases. In some other cases, is not as bad as ridge, and it do approximately the same as lasso when d is very large. But yes, in general, it's a good approximation. So just to tell you very quickly how we use this at work, we were recently trying to model congestion at ports, at like a ocean port, and we had a time series of congestion numbers in the past. So what we wanted to get was, we have no idea how congestion dynamics work. We don't have an equation for that. So what we were doing was just trying to estimate a transition matrix, because we kind of noticed that this process is normally distributed, and we can like figure out how to make it 0 mean, and then we just can use all this process to estimate the transition matrix and estimate congestion numbers, forecast congestion numbers in the future. So this model did better than using just interpolation models. So yeah, I believe it's very useful if you're working with some sort of stochastic processes that require like estimation of future values. So if you work with anything that is kind of related with positioning, times like financial time series, yeah, economics in general, this is kind of really, really useful. So I think that's all I have. So if you have any questions, let me know. We can go over some details that might not be super clear. Yeah, that's it.
What software library or did you do this by hand from implementing your report? suggestions?
Oh no, we were just using Python for this.
Okay.
Yeah, it's just because if you kind of take a look, this is just very simple. We were just using, scikit-learn. Yeah. Yeah, there might be, I don't know if there might be some packages that already implement this, but yeah, we just did it from scratch. They mentioned that they used something in R. I believe it's R, GLMnet. Well, but that was for lasso and simplex. Yes, I believe that's R. But yeah, like calculating this is very easy. And there was a thing with the number of, because we have many different variables that were affecting our congestion numbers, and variables that we had no idea. We were just like letting the data speak because we don't have a mathematical model for congestion. So and we have just like daily numbers, so it's definitely not high frequency time series. So it's not that our dimensionality is much larger than our, like, the length of our time series, but it was still worth to use this method. I mean, this is supposed to be very efficient for high dimensionality. We didn't have high dimensionality, but we wanted kind of to minimize the error and to make sure, because we were making forecasting like 5 days ahead, 15 days ahead, so we didn't want this to blow up at some point.
Did it work?
Yes. Yeah.
The least squares method that you showed at the beginning that you said was expensive. Why is that expensive? I mean, computationally, what's going on there that we get to avoid with this new method?
Yeah, it's just that we are like kind of searching on a large domain. When D becomes really big, like, I don't really have like one of these problems where I have like thousands of variables, but when D becomes really large, so the space that I am like looking for, it's really big. The space of matrices is really big, and the minimization problem just like, it's not that the evaluation of the expression itself is difficult. It's just that searching in this big space becomes slower and slower.
So how does searching that space actually work? Is it like gradient descent or something like that?
Yes.
Okay.
Yeah.
So how much faster like is the new method compared to that?
Oh, they don't mention how much faster. They just like, well, there's a larger, like a more complete paper where they demonstrate the theorem about the lambda zero. They might have numbers on how much faster it is. They are just like kind of showing numbers in terms of error, but no, they don't really show how much faster. In our case, what's very fast because we don't really have like large D, but yeah, maybe it's worth to take a look at the long version of this paper. Yeah, they mention it on the references.
Okay, thank you.
No problem.
Since we're looking at a dynamical system, sort of a natural question that comes up with dynamical systems is stability. Mm-hmm. And so do the authors address any aspect of this? I mean, because you could imagine that the underlying system is like nearly unstable, and then your estimate could kind of trend in, or like, switch over to an unstable system. Do they address this in any way? Do other estimation systems address this?
No, they just like kind of use this constraint here that my time series has to be distributed as like normally with zero mean. So like for this specific class of time series, it's very unlikely that it could lead to instability. So yeah, if your time series kind of becomes crazy at some point and has like huge spikes, and it might be possible that this doesn't work, but they don't really address stability. They just address error bounds. Maybe on the longest version, but we still have to take a look. It's like 43 pages.
Well, I think that might be it then.
Okay, thanks guys for coming.